Okay, so if you watched the previous video, then you saw us derive three equations. These three equations describe uniformly accelerated motion. They all come from this, from an analysis of this linear velocity time graph that we found in our lab extension. And here's the three equations. And if you remember, we found three different equations because each of them lacks one of the variables. This makes it easier for us to solve problems. The first equation lacks the displacement. The second equation lacks the acceleration. And the third equation lacks the final velocity. So moving on from there, there is traditionally a fourth equation which relates velocity to the displacement and lacks the time as one of the variables. Now, unfortunately, if you're watching this video, you won't get to see the experimental evidence for this that I'm going to do in class. You're just going to have to accept it, I guess, or come into class and see the presentation. But in class, we are going to look at the cart rolling down the incline using the motion detector again, like we did in the activity. This time we're going to make a graph of velocity versus displacement. So it's not a time graph, it's velocity versus displacement. And when we make that graph, it's going to look like this, which is called a side opening parabola. Now in class we're going to try to linearize that graph, and we're going to find that in order to linearize it, we need to square the velocity in now units of meters squared per second squared, and graph that versus the displacement in meters. That gives us a straight line. Since it is linear and goes through 0, 0, we know that the velocity squared is proportional to the displacement. Velocity squared proportional to the displacement. So if it rolls twice as far, if it's rolling twice as fast, it'll go 4 times as far. If it's rolling 3 times as fast, it'll go 9 times as far. And the other key thing to pick up, as I show you over here, is that the slope of this graph works out to be twice the acceleration. Now, in order to make this a little more general, we're going to also look at it in class if it doesn't start moving at 0 time. So I'm going to let the cart get going and then look at the graphs. In that case, the velocity and displacement graph will be a side opening parabola, but with a non-zero initial velocity. It'll already be moving when I start making the recording. So when we linearize it by squaring the velocity again, we get a straight line as we did before, but this time it has a y-intercept. That y-intercept represents what the velocity squared is when the position is 0. And the slope is still 2a, and so this is, in other words, the initial velocity squared. The initial velocity squared is what we have on that graph. Now we can make a y equals mx plus b math model out of this graph. The y variable is v squared, the final velocity squared. That equals the slope, but as we showed in class, the slope here is 2 times the acceleration, times the x variable, which is the displacement, or final minus initial position, plus the y-intercept, which is the initial velocity squared. Again, kind of like the very first equation, we can flip these around because its addition is commutative to write it in the traditional way. So if we flip those around, there is our fourth equation. And notice it relates final velocity, initial velocity, acceleration, and displacement. It does not require the time in order to use this equation. So it's very handy. If time is one of the things that's hard to measure, you can still relate the other variables using this fourth equation. Now these 4 equations are very important, and they're given their very own special name. They are called the kinematic equations. You may have seen this prefix before, kine. Kine is Greek for motion. So these are quite literally the equations of motion. But remember that they're a specific kind of motion. These graphs came from, or these equations, came from a velocity time graph which was linear. So these only hold in cases of uniform acceleration. If the acceleration is changing, these equations don't work, and we have to use more complex math. Just to summarize, here are our 4 kinematic equations. And obviously, these are going to be something for you to put down on your 3x5 card for the test coming up in a week or so. And, might be handy for you to have when it comes time to do the next worksheet. So again, these 4 equations: final velocity equals initial velocity plus the acceleration times the time, an equation lacking the displacement. The second equation, final minus initial position or displacement, is 1/2 times the quantity final velocity plus the initial velocity times the time, an equation lacking the acceleration. The ever popular third equation, displacement is initial velocity times time plus 1/2 the acceleration times the time squared, an equation lacking the final velocity. And the fourth equation that we just kind of derived experimentally is the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement, an equation lacking time. So again, this group of equations here is the traditional 4 kinematic equations. Some books that you look at actually have a fifth one, because if you notice here, there is one variable that is in every one of these equations, here, 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 and here. So the initial velocity is in every one of the equations. It is theoretically possible to get a fifth equation that lacks the initial velocity. The mathematical way would be to solve this first equation for the initial velocity, plug it in here in the second equation, and then solve the equation out. But I like the 4 traditional kinematic equations. Seem to be enough for me. So in our next video, I am going to show you how we can use these equations to solve the same kind of problems we just did on the last worksheet, but without needing graphs as a scaffolding.